It's a great pleasure to be here, back at my alma mater. And I also see in the audience my old supervisor for my PhD thesis. So it's nice that he's interested. But anyway, so for many years now, I have been in Australia. And I have been doing some things that I wanted to tell you about. It's a little bit difficult to be the last speaker because everybody covered everything, and all of a sudden I have to talk, and I'm only one step between you and the lunch. So it's pretty challenging, but let's try that. So what I want to tell you about is light, and a lot of things that we heard about earlier from Päivi and Emmanuel and others, I'll be touching upon. But my advantage now is that they taught you a lot of stuff. So I can go into the blue skies and tell you things that you can't understand. I'm just joking. Okay, so what I want to do really is I want to sculpt light in such a way that it will do what I want it to do. And it is in quantum mechanics and also in living cells. So what you see in this slide here, in my title slide, is that I have sculpted light to carry orbital angular momentum, which I'll tell you more about in a minute. And I can trap particles into that. So this is optical trapping that Emmanuel was telling you about in terms of cold atoms. But these are much bigger particles that I'm trapping here. And I transfer orbital angular momentum, and I make them rotate. Why to do that, I'll tell you later. And then OMG does not stand for, oh my God, it's my optical micromanipulation group. And so what we do here is we sculpture light in such a way that we can deliver it into all those points and build a symbol of our liking. And Emmanuel was showing you Eiffel Tower and stuff like that, so let's see what I can do with light. Okay, so outline of my talk is why to use sculpted light, and I think that I have convinced you already that it's good fun. And then I want to use it for optical trapping using optical dipole and gradient force. I want to take it into Bose Einstein condensates, this time made out of atoms, just like Emmanuel was talking about, and show you a little bit of quantum thermodynamics that he also talked about. And especially, I want to bother you again with telling you about the negative temperatures and what happens when you can reach them, what can you explain, and I'll try to explain Onsager vortices, which is a problem that has existed from 1949 when Onsager formulated it. And then I want to switch gears and go to structured light in optical tweezers and then use them in biological systems and convince you that playing with light is real fun, but also a lot of science. All right, so we heard all about Bose Einstein condensate, and I'm just repeating it here, just reminding you what Emmanuel and Päivi have said. And so basically, if we look at the particles around us in the air, they move very, very fast. And when I mean fast, I mean really fast, like jumbo jet. And they can be described as billiard balls. Now, if I lower the temperature, Emmanuel told us that eventually we are observing the wave properties of matter. And if I lower temperature to the critical temperature, all of a sudden those waves form all together one giant wave, and they vibrate with a certain frequency. And that means that we have reached Bose Einstein condensate, and it's a superfluid. And the superfluid is frictionless fluid. We've heard about superconductivity, so now we are in fluid here, which can flow without any friction. So zero viscosity environment. And what we see here is a very old picture of frictionless flow in superfluid helium that people have been studying for a very long time. And then you see it flowing here, and then you're looking at it using interferometric methods. So what we instead do, so we construct the Bose Einstein condensate, and as Päivi said, and she got questioned about it in the Q&A time, how do we know that we got BEC? So we can look at the shape of the atoms as the temperature is going down, and all of a sudden we'll have this humongous peak sticking up, and we'll know that that describes Bose-Einstein condensate, and that means that this thing is my giant wave. Okay, so now I want to take sculpted light of some sort and form. So for example, here we have a round blob of light, and I want to study the superfluid and formation of quantized vortices. So these are small density dips in an atomic Bose-Einstein condensate, and then I want to see how they move around. So that's one system that I want to look at. And the other system is optical tweezers. So they're very similar. It's gradient force it is all about. So what I'm showing you here is I'm shining the laser light, and this is the distribution of intensity around it. And you can see how the forces are acting towards the particle. And here I'm showing you the simulation of what happens when we trap particles into highly focused laser beams. And what we do here is that we can see that the particle is going to the most intense part of the laser beam, and then it wobbles a little bit with Brownian motion there. And if we look at the bottom of this slide, we can see that the light distribution varies quite dramatically when the particle is moving around. And what it tells me is that if I can describe this light, which is scattered by the particle, collect it and describe it, I can tell you what's happening with the particle. Not only its position, but the optical forces and other forces that are acting in the system. So by looking, once more, by looking at this scattered light, it will tell me from which side it comes, how far it came from, etc., and what sort of forces are acting on the particle. Now, this is done with Gaussian beam, so very simple beam, but let's see what we can do otherwise. So what I want to do, again, I want to manipulate light to create these optical potentials to my liking. And in order to do that, Emmanuel said that he had an enormous number of lasers. I don't think he really meant that, because I think that he was using one of those devices in the construction of his Eiffel Towers. Otherwise, there would be so many lasers needed that that would be incredibly expensive experiment. So anyway, so to manipulate light, I can use liquid crystal devices, or I can use digital micromirror devices, which he told you about as well. And he said that there are actually in the projector here, and the projection that you can see is produced by this digital micromirror devices. And so what they do is that I can program both of them in such a way that I can deposit a field onto it that will be created to my liking in terms of intensity and phase of the light. And in terms of digital micromirror device that I'll be using most of the time, what it is, as he said, as Emmanuel pointed out, was just collection of tiny, tiny mirrors, and they can wiggle within certain angle, and I can program each one of those in such a way that I will, at the end of it, have a particular type of light field. If I shine a flat field onto it, in the transmission or reflection, I will get the light in the shape I want. And the resolution of these devices is very good, so they are good to look at tiny little happenings, and I'll show you a little bit of that. And the biggest difference between these two devices is that this is dynamic device. The digital micromirror device is dynamic. It can switch the frames very, very quickly, while liquid crystal modulator is much slower. But they're both very, very good in playing with light. So I want to now take the light and configure ultracold atoms, put them to the potentials I want to have. So now, and the purpose of it is to look at the vortices that I was showing you before. So first of all, how do I configure ultracold atoms? So there are several methods that we can do it with, and one of them is we use magnetic traps, and we trap atoms into these magnetic traps. And it is a little bit hard, if you're using magnetic traps, it's very hard to make it to be microscopic pattern. So in order to do microscopic pattern, we use optical traps, far off resonance. So it means that the atom is not actually absorbing light on resonance and can be conservative, and they are more easily patterned microscopically. However, if you trap magneto-optical trapped atoms, that requires very high power of the laser. So, but we can pattern them microscopically, and people have done a lot of it before. But we can use, as I said, digital micromirror device, and this is what we are doing with our cold atoms. So we laser cool our atoms first, then we magnetically trap them and transfer the atoms, so they are somewhere here, and I transfer them from this glass cell to another experimental cell under very, very high vacuum. And I cool them further there to the critical temperature where Bose Einstein condensate is forming. And then what I do, and those traps, those atoms, Bose Einstein condensate atoms, live a little bit longer than Pavis atoms did. They live many seconds, so we can do a lot of experiments with them. And then I shine a green light and form it to a sheet, and then I come with infrared light, 1064 infrared laser, which is it's coming from my digital micromirror device and is formed to certain pattern. So how do we do that? I first create binary image on my digital micromirror device. Then I project the light. So this is the projection of the light. And then I put my atoms, Bose Einstein condensate, into the ring. Okay? And so the proportion of atoms which are in the ring, which are Bose Einstein condensed, is over 75%. And then, of course, we can play tricks. You were asking yesterday, one of the students was asking whether we can create any potentials. Yes, we can. So here is Bose, here is Einstein. So what I'm doing, I'm doing binary image. I put the light into this binary image, and then I put Bose Einstein condensate into Bose and Einstein. So there you go. So I have dynamical potentials, and I can also create very smooth potentials through atom density feed forward method. So a little bit of advertisement here to answer the question even more. What can you do with the light? You can do anything. And we were also in papers because of that, because it was quantum art. Okay, so. But what is, so Mona Lisa, fish, Australian fish, and my group here who did the pictures. But what is amazing here actually, and I draw your attention to it, is that although it looks grainy here, it really is incredibly high resolution image. Because Mona Lisa's eye is of the order of 1 micron in size. And you can see that we can recognize that eye pretty well. So I think that it shows you that this method of creating potentials is pretty powerful. And of course, you can play further if you want to enter the world of quantum art. So we have Bose Einstein, we saw that. We have Starry Night, Leopard, T-Rex, and then I can play with light and create those images that I showed you before. And I wouldn't be coming from Australia not to show you that I can also create Bose Einstein condensate of kangaroo and do the advertisement for a lot of things. Okay, so but back to science now. So what we can use these potentials for is to create, for example, circuits which are superfluid atomtronic circuits. So I'm trying to make atoms behave like parts of electronic circuits. So I want to have all the parts of electronic circuits, but done out of atoms. So the system that we are using, so here is my Bose Einstein condensate, and the light was coming one sheet of light this way and another one that way, and I formed this potential, which is looking like a dumbbell. And that was something that Emmanuel Bloch showed you yesterday, and he said, if you have this sort of geometry, what you can do, you can fill one of the containers with atoms and then turn the light on and then make them go through the channel here, and they will be oscillating between the channels. And what we also can see here is that there are a lot of black spots here which sort of show me where the vortices are. So by studying the behavior of this sort of atomtronic circuit, I can now create full atomtronic circuit. I won't be showing it to you today because I have a little bit too little time for that, but I can show you how it looks in real life when we're doing the experiment. So what I can do here by sculpting the light, I can vary the size of this container, I can vary the size of the channel, the width of the channel, the length of the channel, and I can start the business running, and then I can move my atoms through the channel and see how they behave depending on the geometry that we are faced with. And by doing that, I will look at the atom transport, but I will also recognize all the elements of atomtronic circuits. And if you're interested in that, I can show you some more stuff about that. So now we go to the absolute negative temperatures, because I want to tell you about them and how I can use them to look at certain problems when the vortices are formed in Bose-Einstein condensate. So as Emmanuel was pointing out, now what is this negative temperature? So let's go through that again. He told you a lot, and I'll just repeat a few little things. So if I have absolute zero temperature, what we then think of is that all motion in matter stops, okay? So that's what we are used to. And now I want to tell you that in our new experiments in ultracold atoms, I can go to negative temperatures. So normally, if I remove heat, then things get colder. And we can see forming of ice crystals here. And they are very well organized when the temperature is very low. So they get colder and very highly organized. And so that means that high degree of order means low temperature. Perfect order, then, we have learned, is temperature of absolute zero. And maximum disorder is infinite temperature. Okay, so let's drive it a little bit further. What about a system becoming more ordered when the energy is added beyond the critical value corresponding to infinite temperature? Okay, and this was what Emmanuel was telling you. It's called negative temperature. I'm adding more energy, and I get perfectly ordered system. So I therefore will call it negative temperature. And all motion is as fast as it possibly can be. So now the average energy of the particles is higher than at any positive absolute temperature of the same system. So this is what we'll call negative temperature. Okay, and this was the pictorial that he also was showing behind some other little overheads that he had. And so what it shows you is the artist's impression of absolute positive and negative temperature. So this is positive 0, and we see that it's the coldest we can get, and we get perfect order here. Then when we go up with the temperature, we can see here that this order is growing, and when the temperature is infinite, plus minus infinite, we have perfect disorder. And then I'm going down in temperature, I'm going to minus temperature, and it means that the hottest temperatures will describe the negative temperature and perfect order. So this is what we'll be trying to do using our cold atoms. So already I mean, in order to get Bose Einstein condensate, as Emmanuel told you yesterday, you need temperatures of the order of nanokelvin, so you are close to absolute zero. So here I have my BC. What I'm plotting here is entropy versus energy of the system, and energy equals temperature, we can say. So what I'm plotting here is absolute zero, plus minus infinity, and minus temperatures, negative temperatures. And what I look at are formed vortices in my BC. And so when BC is being formed, pair of vortices are being formed, and I will show you that in a real experiment. And then as we are going up in temperature, the vortices getting more disordered, as is expected. But when I get to these negative temperatures, humongous vortices, huge vortices are formed. And they persist for a very long time. And so what Emmanuel also told you as an answer to one of your questions was that you can describe temperature as 1 over the derivative of entropy versus energy. And if this is negative, then I will get negative temperatures. Okay, so let us see how it looks in real life. So why is it interesting? Well, in nature, we have these giant vortices, for example, the great red spot on the Jupiter. And the question is, how does it persist? How can we explain the existence of it in time? So in 1949, as I said, Onsager was looking at two-dimensional flows and said that two-dimensional flows lead to vortices piling together into larger and larger vortices, which persist in time. And such state become more ordered as the energy in the vortices increases. So again, we are going towards those negative absolute temperatures. So how do we look at it? Let us skip that. So how do we look at it? I take my Bose Einstein condensate, and I'm forming an oblate potential, and I now will disturb the potential. The atoms are put into this potential, and I will drag a barrier through it with different energies and see how it all behaves. So here we have the barrier being drawn through. And this is what I will see in the experiment, and you can see little vortices being formed. Now I can compare two techniques. I, first of all, can take this paddle steering in high energy injection. And, okay, here we go. High energy injection. And you can see that the large vortices are being formed. So the red one is plus vortex, and blue one is minus vortex. So they are circulating in opposite directions, and then maintain in time. So we are running the time here. So this is just the calculation that we are showing here. And then we go to low energy injection. Oops. Let us go to low energy injection, and for some reason it doesn't want to show. Forget it. Low energy injection would have meant, as it is shown in this picture, that the vortices are spread out throughout the entire optical field. But when the high energy injection takes place, you can see these giant vortices with different signs will persist forever and ever. Well, exaggeration, but they will persist. So clustering is persistent. Vortex-anti-vortex separation inhibits annihilation. Mapping to point vortices reveals high energy. So with that, it is showing you very clearly that the negative temperatures can achieve great order, and that explains the existence of red spot on Jupiter. And we can go further and analyze the results that we got. So here are my vortices of opposite signs. If you ask me how we determine the sign of it, I'll answer that question later. And we can now we can now determine the energy by mapping the point vortices, and we can compare it with calculations, and the calculations, which are based on Gross-Pitayevsky's equation, map the results, experimental results, very well. And so these giant vortices at negative temperatures have been proven and shown. Okay, so let's switch gears from cold atoms and go to warm particles. This is a particle of the size of about 2 to 3 microns, and I'm trapping it in laser light in a gradient force trap. And so what you can see here is I'm moving either the laser light or I'm moving the microscope stage on which the experiment is being made, and I can move this particle in X, Y direction, and I also could move it in Z. But what you can see is that when the particles are not trapped, okay, we repeat it, when the particle, even when the particle is trapped, it sort of wiggles around its equilibrium position a little bit. And if I analyze that wiggle, I can tell you what's happening with the particle in the optical field. And then I can compare it with the particles which are not trapped and look at the Brownian motion. Okay, so I can model my optical trap by assuming a harmonic potential, and we have heard a lot about harmonic potentials before in this conference. And so here I have a particle which is described as harmonic potential, which is wiggling in harmonic potential, and we can see the wiggles in the trap. And I can measure those wiggles. So I have a good camera or some other detector, and I'm looking here at X position, for example, and Y position of the particle, and follow it in time, for a long time. I can then plot mean square displacement of the particle in the, as a function of time, and this is the curve I will get. So I can analyze that and make a power spectrum density, and this is the, as a function of frequency, and this is the typical curve that I will get for my trapped particle. And from this curve, I can now determine role of frequency of the particle and how stiff the trap is, if I only know the size of the trapped particle and viscosity of the medium. So what it is showing you is that I can take highly focused laser light and shine it onto a given object, and I can then trap it in 3 dimensions and dynamically move it in 3 dimensions. And then I can either, when I move it in that environment, I can be interested in probing the environment around the particle, or how it changes when the particle is changing. So I can study all that. But normally what we do in optical tweezers is that it's easy to trap things which are between 200 nanometers to 10 microns, but when they are bigger, it's much more difficult because the optical forces which are acting here are not very strong. They are of the order of piconewtons, so 10 to minus 12 newtons. So if things are getting much larger, it's much more difficult, much heavier, it's much more difficult to manipulate them. The other problem with optical tweezers is, or anywhere where we're using light in living organisms, is that if we want to go deep into the tissue, the light gets scattered, so it's very difficult to put light without modifying the tissue very deep into the tissue. So in my group, we were interested in trying to do something with optical tweezers when it was difficult to do it. Okay, but there was a proper biological question that we were asking. So our objective was to go very deep into the living tissue and then be able to do the trapping, and I would be happy with that. But my biological friends said that, well, we can use it for something really nifty. So what we are doing here, actually, is we are using optical tweezers to interrogate the vestibular system in zebrafish. So first of all, why zebrafish? Several reasons for that. It's a very good animal model for mammalian brain. Secondly, zebrafish is almost, especially if it's very young, it's almost transparent. so it's easier to get light into it. And as I said, vestibular system means, what I'm interested in is vestibular system means balance and hearing. So I want to investigate balance and hearing in zebrafish in such a way that I'm only interrogating balance and hearing and nothing else. So normally what people do when they want to study this vestibular system, they move the whole fish. And the fish is being moved around, and people are looking at the neuronal networks which light up, and I will show you how it happens, and then they draw conclusions from that. But it's a little bit iffy stuff to be doing, because then we're actually not only interrogating the vestibular system, but a lot of other parts of the living organism. So what do? We take optical tweezers. So here is my optical tweezers. Laser comes in. I have double optical tweezers because I can form them to whatever I want. And I put it onto zebrafish. Here's my zebrafish. And at the same time, I have a camera below the fish, which can look at the entire embryo of the zebrafish, as well as fluorescence imaging up this way, where I can look at the neuronal network that is lighting up when the fish is reacting to the stimuli that we are providing using optical tweezers. So let's look at that. Okay, oops, I shouldn't have done that. Okay, so here is our poor zebrafish. It has free tail here, and I'm either putting 2 optical tweezers onto the stones on 2 ears of the zebrafish, or 1 in the time, and we can see that the behavior which we map then in time, as far as the reaction of zebrafish is concerned, are very different if I am interrogating the 1 stone, 2 stones, and the other stone on the other side. And so we can analyze that and see how much power is needed for those signals and how they vary with power, etc., etc. But as I said, what we are most interested in is to be able to see neuronal networks which are absolutely necessary for the fish to actually analyze the signal that is being given to it when the tail is moving. So I have my system. So again, optical tweezers here, fluorescence microscopy there, and light sheet microscopy in the bottom. I'll tell you a little bit more about it. So optical tweezers, I trap and interrogate either 1 stone or 2 stones, and then I look at the behavioral imaging, so I can see how the tail is wiggling depending which of the stones I interrogate. And then I go to a fluorescence imaging, and I use SPIM here, so light sheet microscopy, which I have a special lens which enables me to, where is this? Special lens which enables me to move now the imaging between different Z-planes, and I can see what is happening. Okay, so we are interrogating the zebrafish on one side with optical tweezers, and then we are scanning this set of mirrors here to get the fluorescence imaging and seeing the firing of the brain. And we can analyze that. And if we look at what's happening, analyze those signals, so I can look at the vestibular neurons in zebrafish, and the purple ones are when I am using only 1 trap for a right stone in the ear of the fish, and the green ones are if it's left stone which is being moved. And you can see that there is huge difference which signaling is taking place depending which stone is being interrogated. And I think that this could play as well. Yeah, and this is how it's all done, and I collect the data in 3D, and then I translate it to that, and then I can look at it in 3 dimensions. Yeah, so that was interesting thing to be doing, and I can see Michael standing up, so I will wrap up in 2 minutes, if I may. Okay, So I was telling you at the very beginning that we can also play with light and give it orbital angular momentum. What it means is that the light is carrying orbital angular momentum, certain type. It can be either spin angular momentum or orbital angular momentum. And I think it was Jennifer who was talking about circularly polarized lights, so this is what I'm using here, but I can also use more sophisticated beams which carry orbital angular momentum, so this is Gauss-Leger beams of light, and they look like donuts, and somebody was talking about those donuts as well, not mentioning what they were. So anyway, so I can put now particles into it, into those different lights, and make them rotate. It doesn't want to do it. And I'm in a hurry, so I'll continue. So now, how can I use this orbital angular momentum to power nano and micro machines? So I can do it in such a way that I can sculpt my light to transfer the maximum of orbital and spin angular momentum to structures that I'm interested in. So how I produce those structures, I can tell you in the question time, but here are the results. So for example, I can produce a stirrer here, and you see here the scanning electron microscope picture of it. And what we do with it is that we produce the cog separately from the stalk, and then I take 4 spots of optical tweezers, and I thread the cog onto the stalk, and then I come with orbital angular momentum beam, and I rotate the cog on the stalk. And here is the result of the rotation. So this is how it looks when it rotates. It doesn't rotate very fast, but if we use a little bit more of power, then we can rotate it faster. And here are other examples of machines that we can produce using orbital angular momentum and using a linear momentum of light. And here is basically optical tweezers powered pump. So I'm putting tiny particles into orbital angular momentum beam, and I'm rotating it. And then there is a particle which is coming through, and I can move it around. And here is the red blood cell that I can stretch and look at the viscoelasticity by putting 2 beams of light on each end of it, and then applying certain force to it. And I think that with that, I will have to skip my fantastic microscopic engines. And thank you for your attention. But I can show them later. And thank my group. So these are people in optical micromanipulation group who have done all the work and not me. And here are the people from quantum atom optics group. And thank you very much for your attention.